Good morning, beautiful calculus people. Happy Monday. How were all of your all weekends? Did you have a great weekend? It was a little chilly and crazy out there on Saturday. I don't know if you guys got crazy snow where you were, but like literally it felt like Mother Nature was having a rough day on Saturday. She didn't really know what she wanted to do. It was like a little bit of sun, a little bit of hail, a little bit of snow, a little bit of wind, a little bit of everything on Saturday. Sunday was kind of nice. I was able to get outside for a nice walk on Sunday before it started getting really windy there in the afternoon. But yeah, otherwise pretty relaxing weekend, which was quite nice because I know this week is going to be a little bit of a gong show trying to get some stuff ready, to get stats exam ready and have to get your exam ready too. So it's going to be a bit of a busy week for me. What do we have to do? So we have, I think, just one final assignment that's due, right? So you guys should have finished, I believe, the integral ratio root test. I fixed quiz 9. I know you guys had asked me to fix quiz 9 with the rounding error, so I went back and fixed that. So quiz 9 should be updated for you. Were there any questions that I had to mark in here? I can't remember, and I don't want to show that. Don't want to show anyone's answers off, but I will mark that if I need to mark it, but I have a feeling that one is a self-marking quiz, so quizzes are done. So it'll just be that final assignment that we have left to clean up by Friday. I will start working away, hopefully this week, at the final exam, but let's see what I do have ready to go for you. So I do have some practice exams as well as answer keys here down for you. So this will give you an idea of the kind of style of questions that you should expect to see on the final exam. I do have that YouTube playlist up if you need to go back and review any particular classes. You can go in and try to find the class that you want to take a look at. And then I do have the Zoom call posted up here as well. So for the Zoom call, if you, it's not mandatory to be part of this call, but it will be available from 1 o'clock to 4 o'clock on April the 20th. So if you do have any questions or concerns or have run into something or need some clarification, that Zoom call is there for you to just tune in. I'll be there just kind of marking or doing some work, and you can ask those questions. Like I said, this is going to be an open book kind of final exam. I know I've hopefully said that already to you guys. So the only thing is, I mean, obviously make sure that you're the one writing the exam, otherwise we're going to run into some issues. So you have all of your notes available to you, you have all of the internet resources available to you, barring taking a question and going and asking somebody else to solve it for you. Other than that, you have all the resources you need. You can use Maple, you can use Desmos, I don't really care. All that's available to you. So I'm not going to have a lockdown browser, or I'm not going to be monitoring your screens because it is an open book kind of resource test. But I will be available for those 3 hours if you have some questions. What happened last year was the following. Last year, the multiple choice and short answer questions were put into one section of the final exam. And then last year, all of the long answer questions were put into another part of the final exam. Do I have a, and so what we did as calc instructors is we gave you a template that kind of appeared as the final exam appeared. You could download that template and you could answer the long answer portions on the template. All of the multiple choice and short answer, you could just use scrap paper to do that. You did not have to upload that to any Dropbox or anything. And that's kind of how the exam was structured. So you basically had the short answer multiple choice was about 1 hour of the final exam, and then the long answer stuff we gave you about 2 hours to do that. And then after the exam was done at 4 o'clock, then students would just upload their solution key to the final exam Dropbox as a PDF document or something like this. So this was the style of the exam last semester. I'm still waiting to hear back from our course captain to see what that is going to look like, but I suspect that that it will be roughly the same. So Damien's just asking roughly how many questions. So here, part 1 contained 9 questions for 16 points. That was your multiple choice as well as short answer. That was about a 1 hour, but of course you could finish that early to move into part 2 if you wanted to. Part 2 had 12 long answer questions. It was 44 points. And so same thing, if you have the capacity to finish part one a little bit earlier, that gives you a little bit longer to work on part two. And like I said, this is kind of how we structured it last year. I don't suspect that structure is going to change too much this semester since it's already been done. Why reinvent the wheel? So it will be a decently long-sized final exam, I suspect. If I can cut some questions out to make it a little bit shorter, I will. But because this is a course that's similar across all campuses for all the calculus students, I don't have a lot of flexibility to tailor it too much. I can tailor it a little bit to the content that we covered and make sure that I ask questions really tailored to what we've covered in the class. But I have very little capacity, I think, to remove too many questions from that final exam. Hopefully, I'll know a little bit more. I'm hoping to get maybe a little bit more information by Friday, in which case, if I get some more information, I might host just a small little live class on Friday. If I have some information by then. If I don't, we're probably going to plan, I don't think we're going to need Friday's class. I think we can cover everything by Wednesday to give you guys a little bit of free time on Friday to finish up any assessments you might have. But if I do get some information before Friday, I'm going to pass that along to you as quickly as I can on Friday. So that's all I really have for you right now. I have no new information about the exam other than as I start to get some stuff rolling in this week, I will let you know. Okay, how did you guys feel about power series? Sorry, that's my insurance broker. Please don't call her. How are those extra examples? Did those extra examples, did you find them helpful in clarifying some things? Or did you need more examples, or were those enough to kind of get you started to be able to understand the process of how to find extra examples? Were helpful? That's good. Awesome. So I think just for the sake of us ensuring that we cover the content that is necessary for the exam, we always might have a little bit of time on Wednesday to revisit some topics you want to talk about a bit more. I do want to talk a little bit about some of the applications of power series and why they're important. So let's focus on working on some of that today, kind of seeing how far we get by Wednesday. And if we do have to come back to clarify some stuff, I don't mind doing some extra examples on Wednesday. Just send me an email if you want to see some more examples of stuff. And that'll give me some time to think about and search up some more examples, because I can often make up integrals very quickly on the fly, but it's a little bit harder to make up power series or series kinds of questions on the fly. So we want to look at applications of power series. Oh, yes. Thank you, Colin. I forgot to share my screen. Okay, good. That means you didn't get to see the number of my insurance broker, and I erased it before you were able to see it. Cool. So I'll just chat a little bit as you're copying down the title and the first little sentence here. So you want to talk a little bit about how we can apply some of our previous knowledge to power series. So we know that a power series converges usually inside of a little radius of convergence, kind of inside a little bubble, or sometimes it's called a little neighborhood around the center point. And in fact, most of the time inside that little bubble, it's going to converge absolutely. The endpoints are a little bit tricky, as we saw. Sometimes the endpoints will diverge. Sometimes they'll converge in the general sense and may not converge absolutely. But inside that radius of convergence, we usually have absolute convergence. And that's a really good thing. So if we know that it converges in there, the next kind of natural question to ask is, what the hell does it converge to? So we know we've kind of like manually created this series. We know that it's going to converge somewhere, but what does it actually look like? So what does this function actually look like? Is it possible to connect this series back to something else? If so, what is it? So now that we know when and where a power series converges, we might be curious about what it converges to. In fact, I can't really spell today. I'm having a rough day. So we're going to start today by just refreshing our memory on something that we talked about a little while ago, and that's geometric series. Now, a geometric series looks something like this. We have a kind of starting off point. We have a common ratio. And let's see, I believe that common ratio, let's see, if I put an n here, if I put an n minus 1, I think we can let n range from 1 to infinity. So we have something that looks like this. So this gives us a starting number that's a, right, when n is equal to 1. And then we keep multiplying a by that common ratio. And what we want to do is use our knowledge here. We know that this is going to converge between -1 and 1. And specifically, we know where this is going to converge to. So we have a formula to kind of figure out what this sum would be if r lands inside of -1 to +1. So if we know this geometric series converges, it's going to converge to, I believe our formula was a over 1 minus r. Now notice that if we were to take this geometric series and maybe replace r with x and maybe a with 1, or I mean, we could keep a if we wanted to, we would essentially get a functional kind of formula for this geometric series. So if we take this formula for the geometric series and instead of r, we just put it in x. And we get something that looks like this. And now I have a power series, and this power series converges when x is some kind of fraction between -1 and +1. And we actually know what function this is going to converge to as well. And knowing this information is quite strong. Knowing this, it's often quite possible to help us figure out how to express other kinds of functions in terms of a power series or in terms of a series itself. So let's kind of utilize, I'm actually going to summarize this a little bit. How do I want to say this? I think that's fine. And let's just say this is quite helpful when trying to figure out how to find power series for other functions. So let's actually utilize this idea, try to find some power series representations. And we're going to start with 1 over 2 plus x. Now, the idea here is if I can kind of get it into this form, like this is the form that's important. I want to kind of make it look like a number divided by 1 minus x. If I can get that form, I can convert that into a power series, potentially into a power series. So we know that a over 1 minus x is equal to the following power series. So if we can convert our function into something that looks like a over 1 minus x, we have some hope that we can make this work. So our goal is, we already have x in here, so I want to convert this somehow to make it look like 1 over 1 minus u. If I can do that, then I'm in good shape. So that's step number 1. Let's take our 1 over 2 plus x, understanding that the goal is to try to make it look like this in the denominator. So this is going to feel kind of like what we were doing for arctan integration earlier. Remember how for arctan integration, we tried to make the denominator look like 1 plus x squared? Same kind of thing here. We want to make the denominator look like 1 minus u or 1 minus something. So the first thing we really need to do is we really need to convert this number 2 to a number 1, because this number 2 is not super helpful the way that it is right now. So that's kind of our first priority, is to make this a 1. We're going to factor 2, so this becomes a 1. Okay, let's factor out that 1/2. And that's going to give us 1 plus x over 2. So almost there. The last thing that's preventing us from being able to utilize this formula for the geometric series is this plus sign. I really want this plus sign to be a subtraction. So all we're going to do is kind of group that subtraction sign into the x over 2 by making it a negative x over 2. And that should essentially fit the bill for us. So in other words, we know subtracting a negative is really the same thing as addition. So this is really 1/2 1 over 1 minus negative x over 2. So we get something that looks like this. And the last step here, if you want, we can make a substitution. We can get rid of the negative x over 2 if you want, so that we have something that looks like this. We have 1/2 times 1 over 1 minus u. And if you really want, you could even shove that 1/2 up into the numerator. It doesn't really matter to me. Maybe let's do that. Maybe let's put that 1/2, we'll actually stick that up here in the numerator. So now we have the form that we need. The form that we need is a number divided by 1 minus something. And that's what we have. We have a number a divided by 1 minus something. Okay, so we're going to utilize our formula that was given up here. So using that formula, we do get that our original function, which was 1 over 2x, 2 plus x, sorry, should be equal to, let's see, we should have a series where a is equal to 1/2. We have u getting put in here for x. So we have u to the n minus 1. And then n ranges from 1 to infinity. But we know that u is equal to negative x over 2. So putting that in should finish up this question for us. We have 1/2 negative x over 2 to the n minus 1 from 1 to infinity. So this is a power series representation for the original function that we had. This is a power series representation. For 1 over 2 plus x. So in other words, instead of thinking about the function 1 over 2 plus x, it's quite possible to now think about this series. And we do have to be a little bit careful. It is going to have a radius of convergence given to us by the geometric series. So let me just take a moment to think about what that might look like. So we know the geometric series, the one that we've used to kind of move from, I'm just going to circle some stuff. So we use the geometric series to move from here to here, right? Specifically actually to here. So we've used the geometric series to move from this other form, this other fraction that we have, into the series. So that means that u has to be in between -1 and +1. Okay, so the geometric series says that has to be the case, otherwise we don't have convergence. What was u? U is equal to negative x over 2. And so if we want to, we can simplify this and try to solve for x, and that should tell us the convergence interval for this particular power series. So we could, for example, multiply both sides by 2. And then, of course, change all of our signs at the expense of flipping all of our inequalities. So I mean, whether or not, if I multiply everything by -1, what do I get? I get 2 is greater than x, which is greater than -2. So I guess we get the same kind of relationship at the end of the day, right? We still get that x must be in between -2 and +2. So this would be considered our convergence interval. So if I wanted to use a power series representation, like the one we just found for 1/2 plus x, I could, but I could only use it for x values in between -2 and +2. Okay, so we found the following. Our power series representation is 1/2 -x/2 to the n -1. So we could use this instead of 1/2 plus x. So if we want, we can use the power series representation instead of 1/2 plus x. But we can only do that in between -2 and +2. And so while you're kind of finishing that up and thinking about that, I'm going to pop up Desmos and see if I can show you why this is the case. It's a little bit tricky to do on Desmos, but I think I've done it enough that I might be able to code something in here. I don't really need to code too much, but I think I can get this to work on Desmos. Okay, we have a sum from 1 to infinity. Actually, can I probably shouldn't put, let's see if it'll work. 1/2 times -x/2 to n minus 1. It's not going to like that, so let's put a capital N. Boom. And this can be 1. Cool. Okay. Let's check this out. This is actually such an insane find. I don't know. I always find power series a little bit weird and crazy. So in red is 1/2 plus x. What I've done in blue is I've created a power series based on that expression that we found utilizing the geometric series. So we took our function, we tried to express it as like a sum or the formula we would use for the geometric series that led us to this power series representation. What I've done for the upper bound, instead of putting infinity, I just put a capital N. And that way I can use Desmos to scroll through and basically keep adding terms to this series. And you can kind of see what happens. So right now it's not that exciting. It literally just, if n is equal to 1, you get 1/2. It's not that exciting. So this is a power series centered at the origin, right? It's centered at x is equal to 0. Watch what happens as I start increasing, or I start pressing the play button here. And I'm just going to make this animation go forward, and we're going to maybe reduce the speed a little bit just to like add to the excitement. Here it goes. I'm going to start adding terms to this power series and check out what happens. And notice specifically that the series that we're working with actually converges very fast. And actually, let's decrease this maybe down to like 20. So you can really see it start to form, right? So it's really starting to converge quite quickly, and it converges as n gets larger and larger directly to 1/2 plus x. But notice that the problem that we have is because we're using polynomials to do this approximation, you get this kind of like awkward like thing like this happening, right? So the boundary values of -2 and +2 tend to be kind of the issue, right? Everywhere in between, it converges quite nicely to this function 1/2 plus x, but the endpoints get a little bit wonky, right? Especially the one at 2, because it's bouncing back and forth, positive, negative, positive, negative. But that's the idea. So the idea is, sometimes it's helpful to think about this fractional function 1/2 plus x as a series instead. But you always have this kind of added caveat, this added restriction of it really only works often on some kind of little interval on the real number line. It doesn't always work for all real numbers. In this case, it only works in between -2 and +2. Kind of a cool visual, right? I kind of think this is a really interesting kind of concept. This is really, really cool. So why do I care about that? Well, let's do another example. And then we'll talk about why we care about doing this. So let's try number 2. Number 2 is let's try to do the same thing with 1/1 plus x squared. So is it possible to find a power series representation for this, which is actually the derivative of arctan? 1/1 plus x. So let's try it for this one here. So remember, our end goal is to get a number over 1 minus x. That's our goal. We want it to look something like that. Or actually, we probably really want it to look like this. Because we're starting with an x. So can I somehow rearrange this to get a number over 1 minus u? This one's actually not as hard, I think, as the last one, because we already have the number 1 here. So all we really have to do is kind of get rid of this plus sign. So the first thing we're going to do is try to get rid of this plus sign by subtracting x squared. We're going to change the plus sign into a subtraction, and then we're going to add an extra negative into our x squared. Okay, subtracting a negative is really the same thing as adding. So now, if I want to, I could just say that u is equal to -x squared, and that should do the trick. That's going to give me 1/1 minus u. And then that should allow us to utilize directly the formula for a geometric series, the one that we had up above. Okay, so we're going to use our formula for the geometric series, and we can convert this into a power series. We know a is equal to 1, and we have u to the n minus 1 as n ranges from 1 to infinity. All right, but u we know is equal to -x squared. So let's put that back in. And there you go. Now you have a power series representation for 1/x squared. So therefore, if my function I start with is 1/1 plus x squared, we can think about it as the following power series. -x squared to the n minus 1 as n ranges from 1 to infinity. I mean, we could simplify the powers here if you wanted to. You can potentially show yourself, well, I'm not going to be super fussy about it right now, but you can kind of do some factoring here if you want to, and you can simplify this to make this look a little bit nicer. So the textbook might go through this process of simplifying the powers. But for now, I just want you to know that it's possible to make this representation. I think it's more important for you to understand where this is going to work. Okay, so in order for us to utilize this formula right here, so as I convert from here to here, I know that there's a restriction on u. The restriction on u is u has to be in between -1 and +1, right? So this is the restriction. So that's going to come back down here when I start talking about this function. This function can be represented as a power series, but its convergence is going to be in a little window. Okay, we know that u is equal to -x². Okay, let's multiply everything by -1. Okay, and I'm just going to rewrite this because I like looking at the negative number first. So we get something that looks like this. So the x² value must be in between -1 and 1. And since x² is typically a positive kind of number, we're not really going to be able to take the square root of -1. So we kind of have this idea that the x values are probably going to end up being somewhere in between 0 and 1, because when I square it, it also needs to land in between 0 and 1. So I assume that when we go to look at this on Desmos, we can do this, but maybe the convergence is only going to be on this really tiny interval from 0 to 1. So as you guys kind of finish copying that down, I'm going to bounce back over and just kind of program some stuff into Desmos so we can take a peek and see if that is the case. Oh, this is -x to the -x² to the Okay, so in red, we have the function 1 over 1 plus x². In blue, I believe this is the power series representation that we found for this particular function, utilizing the geometric series to kind of get us there. Now, if I let the animation roll, I am noticing that looks like I have a little bit of a problem in my interval or my radius of convergence. So it could just be something that I messed up algebraically with. I might have messed up with a negative sign. But I can very specifically see that this looks like it's converging on -1 to +1. So it looks like everything is good for this particular function on a little bit bigger of an interval than I had originally suspected. So I suspected 0 to 1. But this one looks like it's going to be OK from -1 to +1. So that might have been an algebraic error on my part, or a logical error. But you can see that action. I think what's important here is kind of seeing that you have this red function. The blue function is trying to approximate that function. It's going to converge to the red function, but it only does it on a small interval. So the power series, it will converge to the function we're working with, but only on a little subinterval of what we're working on. Now, bonus points if someone can figure out where my logical error is, and how do we know that it's in between -1 and +1? Is that easy to see right away? So if -x², I guess this number can be negative, right? This number can be negative. So maybe that's the logical error. Maybe I can't actually. That's interesting. So I think the logical error might be when I multiply by -1 or something like this. But anyway, there is a logical error here. I'm not sure exactly how to bridge the gap here. But it says that this should work from -1 to +1. So it has something to do with this negative sign here. I'm just interpreting this negative sign incorrectly. So my guess is, okay, so if an x value goes in, it's going to get squared first, and then we can apply the negative sign. So x values can go in as negative or positive. The outputs can come out as negatives or positive because of that negative sign. I guess that's okay. I guess that's true. Okay, a little bit of a logical error, I think, on my part. I'm happy with that. That makes sense. So if I'm looking at this particular inequality right here, x values can go in as negative or positive numbers. They're going to get squared, so they're going to turn into positive numbers, but then they're going to get multiplied by that -1. So they technically could still land somewhere between -1 and +1. And the x values that are going to do that are going to be the ones that are in between -1 and +1. So the x values that satisfy what I've circled in yellow actually are the ones that are right here. So if I do start with an x value that's in between -1 and +1, it should satisfy the inequality that I've circled in yellow. That should be true. So I just made a little logical error there when I was simplifying this inequality. So my apologies. So there you go. That's kind of the idea of how I could start potentially with a function. I could try to come up with a power series utilizing the formula for the geometric series. And what I want to talk about is the importance. So why do we care about doing this? So I think this kind of question is a very good question to think about. Like, what's the point of doing this? Why do we care? Especially if the convergence only ever happens on this really tiny kind of sub window. So the last couple examples we worked with, we had a really small radius of convergence. So like, why? Like, why go through all of this process to develop a thing if it's only going to converge here? Why not just use the original function? And we touched a little bit on this when we were talking about functions that don't have an elementary antiderivative. So there are certain functions that we actually can't find an antiderivative for. So if I'm asked to solve that integral, we could try to approximate it using some of the methods that we saw in the approximation section of our course. Or the other alternative is to see if there's a power series representation for that integral. And if there is, maybe we could utilize the power series representation to do some work, because it's much easier to integrate a polynomial using the power law, or to take the derivative of a polynomial using the power law, than it is sometimes to actually integrate or find the derivative. So this is the real importance and the real power, no pun intended, for power series. They make it much easier sometimes to find a derivative, or much easier sometimes to find an integral. So let's take one of our examples up here. And I'll show you kind of how we might utilize this idea. So 1 over 2 plus x. We said that that was equal to the following power series. We had 1/2, we had negative x over 2 to the n minus 1, and n was allowed to range from 1 to infinity. Now I could go one step further. I could actually expand this out a little bit and find maybe the first few terms. Is that necessary? Do I really have to do this? I will in a minute. I will in a minute. But let's think about taking, let's say, the derivative. So what if I want to take the derivative of both sides? Well, over on the left-hand side, we know how to take the derivative using the quotient rule. So the quotient rule says find the derivative of the top, which is 0, multiply it by the bottom, which is multiplied by 0, so who cares? And then subtract the derivative of the denominator, which is 1, times the numerator, which is 1, and divide by the denominator squared. So with a little bit of work, I think we can simplify the derivative of this particular expression to negative 1 over 2 plus x squared. So a little bit of work gets us to that. Now over on the right-hand side, this is actually just like a really big kind of polynomial. So over on the right-hand side, we could find the derivative. We could use the power law. Okay, and the power law goes something like this. I don't really care about this constant. That's still a constant. So what I care about is just kind of finding the derivative of this thing in here. So I could bring the n minus 1 down. I could subtract 1 from the exponent, and then I just need to multiply by the derivative of the inside piece. So I'm doing a little bit of a chain rule here as well. And typically what happens when we find the derivative of a polynomial is we lose the constant term. So you'll notice that the bounds of the summation here will go down to 0. So we lose the constant term essentially. Is that true? That would add 1. This should go to n is equal to, I don't want the constant term. So this actually should be 2, I believe. So yes, that makes sense. Will that lose the constant term on us? That would be 0. We would get let's see. I want to just double check with myself, because power series are always a little bit fussy. I think this is going to be a 2, but like I said, I just want to double check. So if n is equal to 1, we get 1/2. If n is equal to 2, we get 1/2 times negative x over 2. This is my fault for not simplifying stuff so that we could see stuff a little bit easier. So let's simplify stuff from now on moving forward so that I don't screw myself when I try to think about things like this. Okay, n is equal to 2, that should be that. N is equal to 3, that should be 1/2 this thing squared. So as we move forward and take the derivative, we're going to lose this, but we pick up a constant term from here. So yeah, so this n equals 2 should be fine. We are going to get a new constant term by taking the derivative, but we lose the original one of 1/2. So we do end up losing a number at the bottom. We shave off the n equals 1 bit when we take the derivative, but we do end up with a new constant term for the new derivative that we get. So yeah, so I'm happy with this. And this is quite often the the importance or the power that we have with series is sometimes it's really hard to take the derivative, or it's really, really complicated. Like it's a really hard kind of chain rule problem or a really hard quotient rule problem. And it's just much easier to take the derivative of this polynomial thing rather than take the derivative using the quotient rule. So that's quite often helpful. So there is a little theorem I would like to give you guys, just kind of summarizing when we're allowed to do this. And really, when it boils down to it, if you know that a power series converges on some kind of given interval, then you can essentially find the derivative of the power series in that interval, or you could even integrate the polynomial in that integral as well. So there is a little theorem in your textbook that will summarize this up, and it goes something like this. So if your power series has a radius of convergence, that is not equal to 0. So it does have to have some kind of radiance. So it's essentially not just converging at 0. So this just ensures that we don't have f of x equals to 0 identically. So if we have a radius of convergence, then the function defined by the power series can be derived, and we can actually find the antiderivative of this as well. So sometimes this is called piece-by-piece derivation or piece-by-piece integration. Now remember that A is the center point. So A minus R and A plus R represent the two boundary values if I happen to know the radius of convergence. Right, so if this is my interval and I have a center point at A, then I'm going to have kind of an upper and lower point defined by that radius of convergence, right? So this distance from here to here. And if we use the ratio test, right, we can usually find this absolute interval of convergence. So A minus R and A plus R just represent the upper and lower boundary points for that interval. And it's going to be, everything's going to happen super nicely inside this interval. So it's going to be differentiable there. Its derivative is really just given as the following. Its derivative is going to be, take the derivative of this expression and shave off the constant term, right? So we kind of change this boundary value down here because we lose the original constant term, but we just take this derivative normally, right, using the power law. Okay, so that would be the derivative if I have a power series representation. And if I want, I could even try to find the antiderivative as well. And the antiderivative can also be found by doing a term-by-term integration. So in other words, I'm just going to take the expression x minus a, and I'm going to do the backwards power law, which is to add 1 to the old exponent and then divide by the new exponent. So Again, this is just finding the antiderivative of each of these polynomial pieces using the power law. So this would be the antiderivative using power law. Now, when we take the antiderivative, we don't lose any information. So in other words, we don't need to shave off a number from our boundary values, right? Because all of the original information should stay there. But when we do find an antiderivative, we quite often have to add that constant of integration. So it's possible that we could pick up an extra constant term when we go to find the antiderivative. So we're going to add a plus c here just in case. And what's more is that not only can I find the derivative and the antiderivative using this kind of piece-by-piece method of integrating or deriving all of the polynomial components of the power series, but the radius of convergence actually stays the same. So the radius of convergence will not change if I go to take the derivative, or it will not change if I go to take the antiderivative. So provided I know where things are going to converge with the power series, everything kind of stays really nice along the way, which is quite lovely. So that's the theorem that kind of summarizes up the idea. I do want to do a couple examples to show you maybe like a style of question that could potentially be asked. So let's try to find a power series representation for the following function. The function that we want to look for is the natural logarithm of 1 minus x. And I want to use this theorem that we just talked about in order to help us get there. So I noticed that this function that we start with isn't really in a nice fractional form. So it's probably not possible to rewrite this as a over 1 minus u. So that's the first thing we want to notice here. So this is not a fraction. So probably not possible to convert directly to a over 1 minus x. So it's probably going to be really hard for us to do that because I don't really have a fraction yet. So let's think about how I could alter this function a little bit to get it into the form that I want. So can any of you kind of make an educated guess as to whether or not this theorem could be helpful? So I have a function. I'd like to get a power series representation, and the easiest way to do that is to utilize the geometric series. I need to get it to look like a over 1 minus x. Could I potentially start with this function, logarithm of 1 minus x, and take the derivative and or take the antiderivative to get to some kind of fraction? Is that a thing we can do? I hope in the back of your mind you say, hells yes. So if f of x is the natural logarithm of 1 minus x, then hopefully you agree with me that the derivative of this is 1 over 1 minus x times negative 1. So the derivative of this function actually kind of looks like the form that we need. Right, so it's a little bit easier for us to work with the derivative of this function than it is to actually work with the function itself. Okay, so let's work with the derivative. We know that f prime of x is negative 1 over 1 minus x. We should be able to utilize the formula for the geometric series right away. We know that a over 1 minus x is equal to this following series. So n is equal to 1 to infinity a x n minus 1. Okay, a is equal to negative 1. Bada boom. So here we go. Our power series is negative 1 times x to the n minus 1 as n ranges from 1 to infinity. So this is our derivative. But I don't care about the derivative per se. The original question asked me to figure out a power series for f of x. So if I could find the antiderivative of this, that would solve the problem. So we're going to take the integral of both sides. Okay, we're going to integrate each of these terms piece by piece. So each of these x's one by one. Of course, we know by the fundamental theorem of calculus that all of this is essentially just going to cancel out, right? We know that the integral of the derivative or the antiderivative of the derivative should be the function itself. So we get back to our original function, you know, maybe plus or minus a value of c. And we're going to add that c value over here on the right-hand side. So let's see, we're going to have n equals 1 to infinity. And we're going to integrate each of these one by one. So the constant doesn't matter. We are going to add 1 and divide by the new power. And then we're going to tack on our constant of integration. So there it is. There's our integral of that polynomial expression, just kind of piece by piece. So this is a representation for the natural logarithm of x minus 1. Let's figure out what the radius of convergence is. Okay, so the question is, where is this going to converge? I want to make sure I'm using appropriate x values to do work. So let's see. I don't think this is going to, I have a little bit of a problem here, I think, with small numbers, right? So I do need to be mindful of that. And let's see, this works when x is in between 1 and negative 1. And we didn't really alter x that much, right? So x here should work in between negative 1 and positive 1. But the logarithm can't have negative numbers. So that's kind of weird. Is this actually possible to do? Let's try. I'm curious. Based on kind of the logic of the question, I suspect that it's going to be working here. But can I put in those numbers? I don't know if I can put those numbers in. I'm very curious. I don't know. I feel like this could be a problem. Let's see, we got negative 1 times x to the n over n. That's so interesting. It totally doesn't work. Okay, here's what I have. Okay, so in red, natural logarithm function obviously has an issue at x is equal to 1, right? So when x is equal to 1, we're going to have an asymptote. Now, it looks like this power series representation, is it actually going to work? It looks like it doesn't actually work on us. So interesting. I have to walk away and kind of think about why that doesn't work, because it's going to match up with my notes here. Yeah, that's crazy. Weird. So obviously, based on what I'm seeing from Desmos, is that this really doesn't work because I think the original function has an issue for any values that are less than 1 anyway. So this is not going to be a super helpful power series for us to utilize to do work for us, because this is probably, my guess is that this power series is going to work for complex numbers and not for real numbers. Okay, so that's not helpful. Let's do one that actually will work. I know that the one that I have for arctan here is going to work because arctan is defined everywhere. So let's work on an example that we can actually model and see in Desmos. And that is the arctan function. So let's utilize, let's find a power series representation. Let's find one for arctan. And so what I'll do is I'll probably try to hunt down a couple more examples since that last one failed so miserably. We'll finish off the main topic of Taylor and Maclaurin series on Wednesday. So this is kind of like our last technique to develop power series representations for functions. And I'll try to find a couple more, maybe at least one more example where we're using derivatives or antiderivatives to actually find the power series. And so typically when you get a question like this where it's asking you to find the representation and you look at the function and it's not a fraction, it's not an easy fraction for us to manipulate to get to the geometric series formula, we usually want to use the derivative or the antiderivative of this function. So this arctan function doesn't look like it's going to be helpful. So let's work with the derivative instead. Okay, we know the derivative is 1 over 1 plus x squared. And this we can certainly convert into the form that we need in order to utilize that geometric series formula. And in fact, we already did this. Okay, so we know that the derivative, which is 1 over 1 plus x squared, we found a power series representation for that way back here. So I'm just going to go back and grab that. And here it was, negative x squared to the n minus 1. Negative x squared. Now, I am going to simplify this a little bit so it's easier for us to apply the antiderivative after. So I'm going to come in here. Let's see, this is going to go from 1 to infinity. And I'm going to break these apart. So I'm going to break this into -1 to the n minus 1, and then x squared to the n minus 1. Like I said, I just want to kind of simplify these powers a little bit so I don't have to use the chain rule when I go to find the antiderivative. And in fact, with that x squared there, I'd be a little nervous. I might have to do more than the chain rule. I might have to do a substitution or something. I definitely do not want that. Okay, let's multiply these powers together. So we're going to get x to the 2n minus 2. Okay, so here's the simplification process if you wanted to simplify this question way back up there. Simplification is helpful because now I can apply the antiderivative and I can just do the power law on the x portion of this power series. So we're going to apply the antiderivative. Okay, fundamental theorem of calculus says left-hand side just becomes the original function we were working with. Right-hand side, we can integrate term by term. We are not going to lose anything, so I'm not going to change the lower bound, but we might gain a plus c. So I do want to make sure to add that. The negative one's not going to be affected because we're integrating with respect to x. Just the x is going to get affected here. We're going to add 1, so we're going to get a 2n minus 1. So we're going to add 1 to the power, and we're going to divide by the new power. So here is a power series representation for arctan of x. So therefore, f of x equals arctan of x could be represented by the following power series. Now, we might be curious where this will converge. And if we know where this is going to converge, that should actually help us solve for the constant. Can there be more? Yeah, there's actually an infinite number of representations. And the infinite number of representations essentially come from the fact that the boundaries can change a little bit. So yes. So the answer, short answer, yes. Most of the different representations come from the fact that the boundary number can change a lot. But yeah, I mean, there are power series representations we can get from utilizing the geometric series, which is what we're doing today. And then on Wednesday, we'll find power series that are connected to the specialized power series called Taylor and Maclaurin series. And they're found a little bit differently compared to these ones. So yeah, there could be a couple different power series representations for sure. Let's see. So let's figure out where this converges. Well, if we go back up to that previous example we did when we actually modeled this on Desmos, and I had realized I had made a small error, we had the radius of convergence between -1 and +1. So that should still be true. So we started with a power series that had a radius of convergence between -1, or a radius of convergence of 1. So it was convergent between -1 and +1. That should be true after I apply the antiderivative as well. So this new series that we have down here should still be convergent between -1 and +1. So let's go see if that's the case. But the only issue we are going to have is solving for c. So we do need to solve for c, and we can do that by maybe inputting an x value inside of our interval of convergence. So I think we can probably safely input 0 to solve for c. f at 0 is equal to arctan of 0, which is also going to be equal to this series, right? So -1 and -1. And so I'm specifically choosing 0. 0 is typically a really nice number to choose because that's going to cancel out essentially all of the polynomial portions of the series. And we're going to be left with c is equal to arctan of 0. Arctan of 0 is equal to 0. So that means c must be 0. So I can now kind of officially know exactly what this f of x function looks like. And we should be able to model it on Desmos so that we can kind of make sure that everything looks half decent. This is going to be 1 to 0, -1, x over 2, and -1. Okay, so this will be our final answer, getting a power series. Sometimes we would have to add that constant in at the end if we need to. But I'm going to go and jump into the background. I'm going to model this so we can kind of take a look at it and see if it makes sense compared to the arctan function. All right, what do we have? We had -1. Let's just get rid of all of that. 2 and -1. Let's do 2 -1. Good. This one looks a little bit nicer compared to that logarithm one that I so poorly did for us. But here we go. I'm even going to zoom in a little bit so I can zoom out. In red, we have our arctan function. I'm going to zoom in just so you can kind of see what's happening with the series. So here is the series with one term. I'm just going to play that animation and we can see it kind of slowly converge to the arctan function on the interval that we're working with. So remember, the interval we're working with is here to here. So it should converge inside these boundary values. Okay, so inside -1 to 1 should be getting closer and closer to the actual arctan function the more and more terms we add to the series, right? So as we start adding up 20 terms, everything should be nice and convergent there in the middle. All right, so there you go. That's a little ditty on, I guess, some of the importance. You'll probably, if you do take some higher order math courses, you definitely will be using power series quite a bit because they're quite powerful to help us essentially find derivatives or find antiderivatives in a small little neighborhood of where we want to do work. Sometimes it's much easier to use a power series representation than it is to actually find the derivative or to actually find the antiderivative. So that's all I want to show you for today. Like I said, I'll try to cook up another example similar to the ones we worked on today so that you have another example in your notes where it will actually work. Unfortunately, the logarithm one kind of backfired on me because of the domain of the logarithm. And then we'll talk a little bit about the other kinds of ways to find power series, which is the Taylor and Maclaurin series, which are a little bit more popular, I would say, for finding power series compared to utilizing the geometric series. So have a lovely day, guys. I'll stick around for a few minutes if you do have any questions or want some clarification on some stuff. And yeah, I apologize for that example. Work out for us today. Darn. I'll make it up to you on Wednesday.
Hi, Brian. I have a question about the website.
Oh, yeah, for sure. What's up, Hannah?
So it's question 14, and it's like find the mid or find the. Sorry, 1 second. It's estimating using the midpoint rule.
Okay, yep.
So like, I thought I did the question right, but like my answer's not right according to website. Oh, I'm not sure why.
Yeah, I am just going to go in. I'm in the background. I'm just going to go into WebAssign
okay.
and grab your question so I can kind of see what's up, okay?
Yeah. I can send you my work too if you want me to do that.
Yeah, if you want to kind of get that ready and and maybe email that over to me, that'd be great too. And that way I can kind of
Yeah.
really give you a good answer. Yeah, you're welcome, Kate. Have a good day. And Damien, yeah, I'll stick around, and if you want to go over the quiz, we can do that together. Just let me finish up with Hannah here. So let's see. Yeah, if you want to stick around, Nate, I'm more than happy to do that for you too. Okay.
Yeah, I'd like to go over my quiz as well.
Okay, let's get WebAssign all cleaned up first, because sometimes when lots of students want to go over the quiz, it could be an error in my coding or something, so it could get fixed.
Okay.
You said number 14, right, Hannah?
Yeah.
Okay. Number 14. Okay, so it looks like you are good on the first one, a little bit off. Yeah, a little bit off on the midpoint rule, so not.
Yeah, I sent it over to you on email.
On email? Okay, yeah, I'll take a peek.
Yeah.
Okay. It's hard when everyone has a little bit of a different question. So we're reading 11, so 0 to 1 with n equals 4. So let's look at the interval first. So you did 0 to 1, that looks good. And yeah, you got your delta x looks good. So yeah, it's going to be halfway between all of the stuff. So this is going to be 8. Yeah, so 1.75, 3.75, 6.25, 8.75. So those look good. And then it's going to be delta x times everything evaluated here. So yeah, your process looks good. I would suggest making sure that your calculator is in radians and not degrees if you're a physics student.
Yeah, I think it is in radians.
And then so the only other thing you could do to double check is to do the calculation in Maple as well.
Maple? Okay.
Yeah, so it could just be that you're entering something into your personal calculator incorrectly. So I would just type it out into Maple or even into Desmos, or like just kind of verify it with another calculator.
Right.
Because you're very close to the final answer. And based on your work, I can't really see which one is what's incorrect, unfortunately.
Okay.
So yeah.
Well, that's okay. As long as I'm on the right track, I'll just recalculate it.
Yeah, exactly. And I think it's probably just an error in maybe one of the decimal numbers that you calculated or something like that.
Okay. Okay, thank you.
Yeah, you're welcome. Okay, so we want to look at some quizzes. Well, can you guys let me know in the chat what questions, or did you want to kind of go over the quiz in general? Question 5 for key, okay. Just the last question, okay. Okay, so Key, Hannah, who else is here? Damien's here, and Nathan is here. Nathan, did you do this quiz? Are you trolling me?
No, I didn't get to do it, and I was going to ask if I could do it today.
You're asking a lot.
I know. I'm sorry. I thought you said Monday on the
instead of
last. Yeah, and then I looked at it today, and it was like, it's going to do it after my physics class, and it was like, you're not allowed to do it. And I was just wondering if I could do it today.
How could you put me on the spot like this? All these other students. Okay. Let's see, what can I do? See, the only problem with letting students do stuff afterwards is now I have to go in and make sure that everything is closed.
Sorry, my house is like under construction. And I was also wondering if we could go through the quiz before that one. The last 2 questions on it.
Nathan, can you make me a promise that you're not going to reach out to any students to look at what they wrote down for final answers?
Sorry, I couldn't hear you. What did you say?
Can you make me a verbal promise that you will not reach out to any other students and ask them for answers to the quiz?
I won't do that, I promise you. I don't even know anybody in the class.
Hey, you know me. That's not very nice. Okay, I will, let's see, I need to put an override in for you. Yeah, that is very true, Kia. Okay, Nate Parsons, what is today? Today is the 12th. I will make it open for 30 minutes until tonight at midnight. Tonight at midnight is your due date. Okay, go do it.
Thank you so much.
We'll talk about your last quiz on Wednesday. Just remind me Wednesday after class, and we'll take a look at your quiz then. And that way I can kind of focus on the students here right now.
Okay, thanks.
Okay, Key wanted to look at question 5. Question 5, Mr. Key. When applying the ratio test has to be positive, my dude. So it's an absolute value. So the limit that we get should always be a positive number. I will upgrade your mark to 1.5 out of 2, but that limit should be a positive number, that's all. You have the correct limit and you have the correct interpretation of that limit. Just has to be a positive limit. Cool, that was an easy one, okay. Okay, that's done. Hannah, number 3 for Hannah, 1, 2, 3. Let's see, cosine squared of n, 1 plus n squared. Okay, I can probably show this to you on Desmos and we can kind of get an idea of why this one doesn't work. Let's just leave and open up a new one. Okay, cool. So Kieran, you're wondering the same thing. So let's take a look at what cosine squared. Actually, I think Desmos wants the squared afterwards over. So it's really a matter of kind of like looking at what this function does. 1 plus n squared, 1 plus x squared. So here's the function that would match up with the series. So it definitely looks like it's not always decreasing. So one of the things we need to select is that it's not always decreasing. It is continuous. So based on what we have, it is continuous. Sorry, I didn't mean to show that screen there, guys. I'm not recording anything. This will not get posted up to YouTube. It's definitely continuous. So I'm not worried about that, but it's not decreasing. And sometimes it hits the x-axis. Right, so there's a couple like values where it's actually going to bump onto the x-axis. So this function isn't always positive either. So that's the other thing. You wanted to select it's not always decreasing and it's not always positive. So we can't apply the integral test in this case.
Okay, that makes sense. Thank you.
Yeah, you're welcome. Yeah. So 0 is a weird one, right? So as soon as you hit the x-axis, as soon as you kind of bump off the x-axis like this, you can't use the integral test because it's not a positive. It's not an always positive function. Yeah. 0 is neither negative or positive. Yeah. And I mean, with regard to the integral test, you can think about it as a negative number too. Yeah. So as soon as you hit 0 or a negative number, you just can't use the integral test. It's impossible. So is that the same for you, Damien? The same question? Oops. Here's a question 6. Okay. Let me jump back. I'm just going to jump back to here so that I can take a peek at what your answers are. Okay, number 1, 2, 3, 4, 5, and 6. Okay, so I can give you some partial marks because you definitely concluded B correctly. So I'm going to give you 1 mark, 1 mark back for having the correct interpretation of the test. 32 was 2 to the power of 5. Why don't we actually do this together? I think I might actually have solved this. I may have solved this in Moodle, so we can check through my unfiled notes and see if I have this somewhere. That's all statistics and gross. That's math for elementary teachers. Math for elementary teachers. Do I not have this anymore? I thought I solved this question somewhere. Guess not. Okay, well, let's do it anyway. Since y'all are curious about it, let's see how we get. And if you're getting negative 32, it's probably just because you're misinterpreting the absolute value bars. So this is negative 2n, so negative 2n over n plus 1, n plus 1 to the 5n. So this is our a sub n. And this is because we have n as the base and as the power, this is going to be a root test kind of thing. So the root test says, look at the limit as n gets really big of an under the root, but we have to take the absolute value bars. So the absolute value bars are needed for the root test here, especially since we have a negative 2. We're going to get something that looks like this. Okay, so instead of writing like the rounded brackets, I'm basically just going to throw in the absolute value bars here. Because if I can absolute value the base, then the power part doesn't really matter. So essentially, we're just going to kind of keep collapsing the absolute value bars in as far as possible. And I know here that n is positive anyway. So n over n plus 1 has to be positive. So the only thing I'm really concerned about inside the absolute value bars is going to be the negative 2. So I'm actually going to distribute the absolute value bars directly to that negative 2. And then everything else can kind of pop out of the absolute values because I already know it's going to be positive anyway. So we kind of get something that looks like this. We get like this, 5n under the root. And so what's going to happen is we're going to essentially exchange this negative 2 for a positive 2. That's where the positive comes from inside of our root test. And hopefully we'll get 2 to the 5, I think, once everything has settled down. So we're going to get 2n plus 1. And the square root and the n are going to cancel, and we're going to get this to the power of 5. Okay, so everything should, I think, probably match up with what you guys have now. Yeah. So you're going to get like, this is going to be 2 to the 5. The rest of the stuff's going to tend towards 1. And that's where your 32 comes from. All right. So you can kind of distribute the 5 through the brackets, or I guess you can even like put the limit in. That's maybe what I would do, is you can kind of put the limit in, kind of figure out where this limit's going. This here is tending towards 2 as n gets really big. So you just get 2 to the 5. But yeah, so I'm guessing if you got negative 32, and for those of you that are still on, if you got negative 32 and the overall mark that you got was 1.3, I'll go back and I'll adjust it to 1.5 if you want me to. So just send me an email if that's something that happened. Or I think Damien, you had one where it was like you put in 1 because maybe you just didn't know how to put the negative 32 in or something. Right? Like if you input a number and you think you had the right interpretation of the test, maybe I should just do this for everybody. Just someone send me an email just to look at the quiz, and I'll go back and I'll remark some of those questions. Because if you put the wrong number in but had the right interpretation, I will give you marks for having the correct interpretation. So just email me. I'll go look at the quizzes and adjust some of the marks for these tests. But hopefully that gives you at least an idea of where the final numbers come from. All right. Yeah, you're welcome, guys. No worries. I will see you Wednesday.